So we will start in a few seconds. It is just live streaming. Yes. Namaskar and very good evening from India, and welcome to the keynote session 4 of the virtual conference on disaster risk reduction, civil engineering for a disaster resilient society. So without taking much time, let me introduce the chairman of this session, Professor Chandan Ghosh. He has been serving National Institute of Disaster Management for a long time, and he was on deputation to IIT Jammu, and he is now again back to NADM. If I understand correctly, he holds 2 PhDs, one from IIT Kanpur and another one from Japan. He also did postdoctoral research in Japan, and his work in the area of geotechnical earthquake engineering, reinforced seismic micronization, ground improvement, and more importantly, bioengineering and ecosystem-based disaster risk reduction is very popular, and you can see him very passionate about disaster risk reduction, and voluntarily he goes to the field, and his social media posts also have helped a lot in creating a lot of awareness among the common public. And his innovations and creativity in delivering the message is very unique, and he has published several papers in reputed journals and conferences, and he has a lot of awards to his credit, like Best Doctoral Thesis in 1993, and several other awards like H.C. Verma Golden Jubilee Award and Lifetime Achievement Award by the Indian Geotechnical Society, Delhi chapter, etc. And he is also the chairman of this conference. So let us welcome Professor Chandan Ghosh, and I now hand over the session to Professor Chandan Ghosh. Chandan sir, please.
Thank you. Welcome. Thank you, Sival sir, for taking this leadership role for almost 4.5 months, and also taking this conference in the middle. Now we are on the 3rd day, and with all efficiency and with all warmth that we have received from participants and our keynote speaker, and also technical session coordinator as well as speaker. So this is the keynote session 4, and in this session that we are having 4 keynote speakers from different fields, and among them that I'm happy to see that the cyclone expert from Indian Institute of Tropical Meteorology, IITM, where Dr. Roxy Matthew Cole, he is a climate scientist, and so cyclone part that he is going to tell that how over the years, last 5 to 7 years especially, that we have improved, and where IMD became a IITM and IMD in Delhi, and also this the weather forecasting that research organization in Noida, Delhi, under Ministry of Earth Science. So Roxy is currently leading research on climate change and how it extends to the rapid warming in Indo-Pacific Ocean. So he is the chair of the Climate Variation and Indian Ocean Region Panel and lead author of the IPCC reports. So welcome, Dr. Roxy, and now I would say that please, you will have, I think timer is on, no? timer is on, so I request now Roxy, Dr. Roxy to have that 20 minutes, 22 minutes of presentation today.
Thanks a lot, Dr. Srivalsa, for welcoming us all in and inviting to this beautiful session. And thanks, Professor Chandan Ghosh, for very beautiful introduction. I'm happy to see so many participants over here ready to listen on how about cyclones, tropical cyclones in the Indian Ocean, and how it is changing with the changing climate. So let's jump into what the cyclones have for us. So I guess you can see me on full screen over here.
Yeah.
Yeah, perfect. So cyclones is a hot topic across the tropics. That's why we call them tropical cyclones, but it is much more of a important topic for the Indian Ocean. Why is it so? And you know that cyclones form over the warm waters of the ocean, right? And considering that these oceans are changing over time, how does this cyclone characteristics change? Will it affect us over India and South Asia and other parts of the Indian Ocean rim? That is what we are going to hear today in this talk titled Cyclones in the Indian Ocean. Now, I am Roxy Matthew Cole from the Center for Climate Change Research. It's a center in the Indian Institute of Tropical Meteorology. It's located in Pune, and it's under the Ministry of Earth Sciences. So coming to the cyclones, why it is important? Cyclones are one of the most severe extreme weather events, especially for South Asia and India. And this is a map that tells you where in India the number of deaths due to different extreme weather events are the largest and what kind of event it is. So generally, most of India, you can, if you look at the map, it's categorized for different states, and you can see different pie charts belonging to different extreme weather events: cold wave, heat wave, lightning, floods, cyclonic storms, etc. And most of the regions face floods, and some of the regions like the east coast of India face an extreme threat from cyclones. You can see the cyclones are the largest threat across the east coast. And what about the west coast? Some regions like Gujarat and Kerala have some threat from the cyclones, and recently Maharashtra also. And is this changing? Are we going to see more cyclones on the west coast, and why? So this is what we are going to see, and how it is related to the oceans surrounding India. So if you look at the statistics, cyclones, floods, heat and cold waves and lightning, all together they have taken about 1.4 lakh lives during the last 60-70 years. Actually, during the last 5 decades. Last 50 years, 1.4 lakh lives from these extreme weather events, which is why understanding these cyclones are quite important. And this is going to change further with global warming. So this is a picture from the IPCC Special Report on Extreme Weather Events. So what they are saying is that there is the exposure to cyclones across the globe is changing, but it is quite larger over Asia. So these deep brown colors are the figures for 1970, and these are, mind you, these are in thousands. Okay, so if you look at that, around 68 lakhs of people were exposed to cyclones in Asia in around 1970s. Now that's going to change. By 2030, it is going to be 1.25 crores. Now that's a huge change, and this is because not only just because of the number of cyclones, actually the number of cyclones over this region is fewer compared to many other regions. So why is that? It is because we have a high dense population over here, and also we have less means of early warning systems compared to other regions. And if you look at the other regions like Africa, North America, the changing exposure is much lower, right? So more reasons for why we need to focus on cyclones and how they are changing. Now, I talked about the number of cyclones in different regions. So this is here we have clearly classified how many number of cyclones happen in each basin, each ocean basin. So if you take the entire southern hemisphere, around 29% cyclones occur over there. And most of the cyclones occur over the Northwest Pacific region. You might have heard about cyclones hitting Philippines and other countries over the East Asian region. So these are from the Northwest Pacific cyclones. Now, if you consider the North Indian Ocean surrounding India, they contribute only 6% of the cyclones, of the total number of tropical cyclones. Bay of Bengal 4% and Arabian Sea 2%. These numbers that are given here is the total number of cyclones that occurred in the last several years. So what is the point here? Though Arabian Sea and Bay of Bengal together contributes to only 6% of global cyclones, it contributes to in case of the number of deaths, human loss, it contributes to 80% of the fatalities. Now this number has come down recently due to improved forecast and disaster management, but if you look at the last 30-40 years, last few decades, this is the state. Now I mentioned that tropical cyclone forecasts have improved over time. So if you look at the earlier period, like in 1999, one of the strongest cyclones hit the Odisha coast. This is the Odisha supercyclone. The number of fatalities were more than tens of thousands, right? Not only in Odisha, but other states and parts of neighboring countries also. So because of improved forecasts and disaster management at the ground, these fatalities, we have brought down this number from 5 digits to 2 or 3 digit numbers, right? And that is because the forecast of the track has improved, the track has improved, forecast of the landfall has improved, and also the forecast of the intensity of the cyclone also have improved. So this is a picture of how the forecast skill has improved over time during last 15-16 years from 2003 to 2019. So this is the landfall point error in kilometers. So in the recent years, we have got a quite good skill in forecasting this cyclone landfall in about 24 to 36 hour lead time, right? So we have quite improved in that respect. But there is a catch here. These cyclone characteristics now are becoming erratic and unpredictable. Why is it so? Well, to understand why it is changing, we need to know what drives these cyclones. Cyclones derive their energy from the warm waters of the ocean. So more warm water, there is more convection going up, and moisture and warm air, it helps the cyclone to intensify. So because of that, cyclones generally occur in the warm pool region. So now what is a warm pool region? You can see this Indian Ocean where I put these colors, these warm red colors. Those are the warm pool regions. So here the ocean surface temperatures are permanently above 28 degrees Celsius. So that's why it's called a warm pool region. So cyclones generally occur in this region. And you can see the warm pool region in Bay of Bengal is much larger and much stronger compared to the Arabian Sea region, especially the Western Arabian Sea, Western Indian Ocean region. It's cool, right? Compared to this warm pool region. This is one reason why there are more cyclones occurring in the Bay of Bengal compared to the Arabian Sea. So in a year, maybe there are 2 to 4 cyclones occurring over the Bay of Bengal, while there are sometimes there are no cyclones in the Arabian Sea, or sometimes there are 1 or 2, barely 2 cyclones in the Arabian Sea. But now that is changing. We are seeing more cyclones in the Arabian Sea, like recently Cyclone Nisarga hit south of Mumbai, right? That was a strong cyclone, and that too during the monsoon onset time. Now, generally cyclones don't form during monsoon. They form during the pre-monsoon before June, like April, May, or the post-monsoon, like October, November, because the monsoon winds are not favorable for cyclone formation. Now, that's all changing because this warm pool is expanding. Warm pool temperatures above 28 degrees Celsius is expanding. Now, why is that? Because of global warming. Why? Because oceans take up 93% of the heat from the global warming. Now, oceans have a particular characteristics. They are a big, deep reservoir of a liquid with high heat capacity. So if some of you have studied physics or the fluid properties, you might know that water has high heat capacity compared to land or air. So because of that, water can hold more heat for a longer time. And this ocean water has been absorbing the additional heat from the emissions due to emissions for a long time. Now, how much is that heat? Imagine all the electricity that we produce yearly and multiply it by 150. That is how much heat oceans absorb every year. And because of that, the temperature over the Indian Ocean is also changing. So what you see in colors here are the temperatures, okay? The change in temperatures. So generally, you saw the earlier map with temperatures with around 28, 30 degrees Celsius and all. Now add these anomalies over that. That is the change that we see since the 1950s. So some of the regions are showing a temperature change of up to 1.2 degrees Celsius. This is much larger than global average temperature rise, which is around 0.9 degrees Celsius. So that means the cyclones will also change. So I told you that we are able to forecast the track of cyclone, landfall of cyclone and all, but there is one characteristic of cyclone that we are unable to forecast. That is the rapid intensification of cyclone, and that is happening now more than ever because of climate change. So during the last monsoon onset period, we had two back-to-back cyclones. One was Cyclone Nisarga on the west coast and the Cyclone Amphan on the east coast. Cyclone Amphan intensified from a Category 1 cyclone to a Category 5 cyclone in just about 18 hours. So Category 1 is like 100 from 100 to 150 kilometer per hour speed, and Category 5 is like 200 to 250 kilometer per hour speed. So in 18 hours, if it intensified in 18 hours means that when we went to sleep, it is like a Category 1 cyclone, very weak or moderate cyclone. But when we wake up from bed, it's a Category 5 cyclone, very intense super cyclone, and it's going to make landfall. So this kind of rapid intensification, the forecast models are unable to pick up. It's not just the case of Indian Met Department, it's the case of all global models. Because climate change presents these new challenges for forecasting. And this is because why it is intensifying rapidly? It's intensifying rapidly because of very high temperatures. Now, this is the average temperature which should have happened just before Cyclone Amphan. Yeah, this is a climatological ocean surface temperatures around 28, 29 degrees up to 30 degrees Celsius. But this is what we witnessed just before the cyclones. That is around 31 to 33 degrees Celsius. That's like super high temperatures. And that has the characteristics of a marine heat wave. So what is marine heat wave? That is a new term, very new term I'm introducing to you, and which has not been much popular a few years back. Marine heat waves are heat waves over the ocean, just like over the land, just that they are over the ocean. So if this blue line is the mean sea surface temperature, SST is the sea surface temperature during April, May. This black line is the temperatures that we witnessed just before Cyclone Amphan. Cyclone Amphan is marked here, right? And this green line is the 90th percentile, which means these temperatures are even above, are in the top 10 percentile of temperatures ever occurred over this region. So if you compare it to the mean sea surface temperatures, the change is around 3 degrees Celsius, almost 3 degrees Celsius warm as sea surface temperature anomalies. So these marine heat waves are driving this rapid intensification of cyclones. Now, here is a picture of the sea surface temperatures before most of the cyclones which occurred during 1980 to 2020, last 40 years. So you can see that generally in the earlier period, so we have for pre-monsoon period in Arabian Sea and Bay of Bengal, post-monsoon period for Arabian Sea and Bay of Bengal. So generally earlier period, the sea surface temperatures were around 29 to 30 in Arabian Sea and similarly for the Bay of Bengal. But now it is about 30 degrees Celsius for both the basins. And similarly, it has increased for Arabian Sea also. So this helps in this rapid intensification. So generally the temperatures in the Indian Ocean has increased by 1.2 to 1.4 degrees Celsius. And that is triggering more storms and cyclones in the Western Indian Ocean also. Now this region is also becoming a warm pool, yeah, which means it is this warm pool temperatures are expanding. And this has impacts in not unimaginable ways. Even the locust storms that we saw earlier in North India were a repercussion of these kind of increasing temperatures. So what happened? So generally this is a cool region, it doesn't support convection, but now it is supporting more storms because the temperatures there are increasing rapidly. So that triggered a lot of rains in the east of Africa and triggered unseasonal vegetation over there, leading to breeding of these locusts, which moved on to the north along with the moisture and winds over the Arabian Peninsula to North India, to the Indo-Pak region, and spread all over this region where they found favorable conditions, right? So this is one kind of event where these storms can lead to changes in changes and impacts across the Indian Ocean Rim region. And this is an example. This is a snapshot from just one day in December 29. It's a feast of storms in the Western Indian Ocean, where it was not a warm pool earlier, but now it's a warm pool and supporting a lot many storms, like 1, 2, 3, 4, 5 storms in a day. It doesn't happen like that. So these kind of storms have a huge impact. Now I'm coming on to the last session of my talk. It's not just the cyclones. Cyclones sometimes co-occur with other kind of events as well. So that is what we call compound events. Now this is also a new term. We have heard about extreme weather events. Now what are compound events? Compound events are when multiple extremes overlap each other. Now this is a picture, comic picture from India, where we have to face multiple events all together, right? So you have the rains happening from on top, you have the water splashing from the base here, somebody spitting over here, there's already water on the floor. So the situation for compound events also is like that. Now this is a case, this is a schematic picture of how compound events act together. So suppose we have a cyclone over here, a strong cyclone. It will result in storm surges and strong waves hitting this city, right? And suppose this is superimposed on a rising sea level. So that increases the impact of these waters coming in. And if there is a high tide also, there is more water pumping in. Now consider that these cyclones are coming with heavy rains also, because the rainfall amount with global warming, there is more moisture available, more rains are coming in with cyclones, and cyclones are spending more time over land also. So which means there are heavy rains also. And if it is a city like Mumbai or Kolkata or Visakhapatnam, where cyclones have almost raised by in the near time period, it can damage the city because these multiple extremes are acting together. So that is something we have to work together. Already ministry and the World Meteorological Organization, they're working on flash flood guidance and all in terms of not only for cyclones but also heavy rainfall events. On an experimental level, they're trying that on Mumbai, and if it works, hopefully it will be replicated in rest of the country and South Asia as well. Now, there's a huge benefit for having this, managing these disasters and having early warning systems. So this is the economic impact assessment of the forecasting that we are providing from the Ministry of Earth Sciences. So what they say is that there is a total expected economic benefit in 5 years of 50,000 crores. So that's about rupees 50 for every rupee spent, which means that we need to invest more in this kind of early warning systems and spread it across South Asia. Now, we commit more than that we are really investing. So we need to act on our climate change policy also in that respect. So India has committed for about 100 gigawatts of solar power and other renewable resources by 2022. But we have reached only barely 30 gigawatts. Now, this is appreciable. I mean, we need to appreciate that India has done up to that, but we need to follow up on that and stick to our climate change policy rather than making commitments alone and opening up coal mines. Yeah. So that is all from my talk, and I thank all my collaborators. We have a lot of collaborators. We have a climate research lab at IITM with my students and other scientists in the team. And we have an Indian Ocean region panel and Indian Ocean team network, which work on these extreme weather events and observations in the Indian Ocean. We have a team on the IPCC that work on these climate change reports, which come out periodically. And we also have declared this coming decade as the UN Decade of Ocean, right? Cyclones form in the ocean, and it's a key factor for us. And we hope to understand more of the cyclones, monitor more of the cyclones, and work towards it. And thanks to NIT and all the organizing team for organizing this wonderful talk. Thank you. Thanks for listening.
Chandan sir, please unmute your mic.
Yeah. Thank you, Dr. Raksi. So you have rocked really you have rocked, or you have shown that to most of the civil engineering that who are participants over here, and also from cross section of the society, what cyclone is and how it is being monitored, and how your effort, individual effort, as well as team effort that you have been making with the WMO and IPCC and the reports that you are bringing in. I think it gives really a focus to civil engineer who thinks that we make the society, we construct, so we are resilient and a lot of things. But here we can see that lot of scope is there to, especially the 3D photo that you have shown with the umbrella, that we have to protect ourselves in this earth, and with all the observations and quality of the data that you have shown, and the kind of temperature that which are changes that taking place in the ocean, and it is really you have opened up a fantastic domain for the civil engineers beyond typical civil engineering studies. So thank you very much for being with us, and
Thanks,
I can see just quickly some of the queries raised by participants. Quickly, only 1-2 minutes. Okay, there is one. What are the toolkits you have used to generate this data, sir? Somebody, Dipti. And what is the baseline data for you? I think you can reply these things in the chat box, which you can see, because we are having shortage of time. And also, I just mentioned that another from SM. Anas, why did Tamil Nadu only 50 cyclones experience least number of cyclone landfalls along the east coast? So the same thing happened in the case of cyclone Gaja. So these things I request you to kindly respond to everyone, so that we can also note whatever extent possible, or by communication or showing some linkage to our participants who are sitting there. So with this, I would,
thanks a lot.
thank you very much on behalf of VCDRR committee. Now I call upon our next speaker, Dr. Alistair Burnett. He is having long experience in modeling water infrastructure projects worldwide, and he provided technical reviews of international modeling in WWDR 2020 Water and Climate Change Report to the United Nations. He has been commissioned for feasibility modeling reviews by institutions such as World Bank, Asian Development Bank, and the European Investment Bank. In fact, he is currently chairs the Flood Risk Management Technical Committee of the IAHR. That committee is now investigating weak points in international engineering practice for the management of river and coastal flood risks through climate change in 21st century. So today's topic is mainly on coastal flood and tsunami flood or due to tsunami flood, which he is going to explain. So let us welcome Dr. Alistair for his presentation, and welcome. Now it is for you.
Thank you.
Yeah.
No.
Yeah, sir, should I share the screen from here for you? I can
Yes,
share your screen.
Yes, if I can share the screen.
I hope it is visible. I hope it is visible.
I cannot see it yet. Just a minute. Yes, there we are. Thank you. Everyone else can see that. Well, good evening. Good morning in my case, from New Zealand. As you can see, it's dark outside. It's a real pleasure to be here and to hear that there are so many participants in this audience from all over the world, and of course, especially from India. I have been to India a few times and always enjoyed my visits. So the previous talk actually led on very nicely. I congratulate the organizers for putting the two talks together, because the last part of that talk particularly talked about the problems facing cities with inundation from floods, storm surge, and so on. I am going to talk about a third dimension of the flood problem this time, although our committee deals with river floods and storm surge flooding, cyclone flooding, if you like. And also the third dimension is the tsunami flooding. And India possibly doesn't have as much risk there as perhaps a little further south in Sri Lanka and so on. But it is something that many cities have to consider in addition to the other flood risks. So what's happened here? I need to start this somehow. You can tell me next. I will move the slide. I beg your pardon? Can I start this somehow? Where's my screen gone?
Yeah, please. Whenever you whenever you instruct me, I will move the slide. You can just tell me next. I will move the slide.
Well, that's going to be a bit complicated. Can I not run it from my end here? Or is that not possible?
That would not be possible because I am sharing on for you.
All right. Thank you.
Can, yeah.
All right. So I'll have to just say click or something when I want to click from the mouse click, if you please. So First, development of flood risk management, general background, that evolved with human habitation over thousands of years based on a need to avoid frequent flooding of living floors. So the key thing here is the relation of water levels with the level of the floor, which is a fixed level once you built the building. So inland settlements had to understand drainage in terms of discharging to a lower downstream level along rivers, while coastal people had to learn that gravity waves, especially tides, may periodically raise that downstream level. And so there's a difference there. Click, please. Click, please. Thank you. There is an overlap area between the river and the coastal people, in which the Hong Kong drainage authorities introduced this term, the fluvial tidal zone, which is a good one, I think. There you have to raise floors above both high tide and flood level, and in extreme cases such as Hangzhou in China, the rising tide may form a bore wave with an incoming hazard comparable with the largest urban tsunami. With the late Holocene sea level stationarity, empirical methods have been able to contain the risk of Hangzhou in the past century, but click, please. Click, please. And again, thank you. So now we have to face the end of Holocene stability of sea levels, as well as increases in storm intensity. So we've got these higher storm surge hazards, as mentioned just in the previous lecture, as well as greater river flood discharges. So Hong Kong, where I have worked with the Drainage Services Department there, they have responded by proposing concurrent analysis of the two cases, and they have described it quantitatively as extreme sea level in conjunction with heavy rain and high sea level in conjunction with extreme rain. So you've got both sea level and heavy rain, but they aren't going to both be at extreme levels at the same time, or the probabilities are very low of that. So the quantitative answers depend on time series analysis of historical records. So you can actually go from the qualitative extreme, high and heavy to a return period. Hong Kong practice does not extend to tsunami flooding, because they don't have significant tsunami hazards there. But in coastal communities with a history of tsunami flooding, there needs to be management of that kind of inundation at the same time as the other floods. Click, please. So we're proposing a methodology by which all flood hazards can be treated in parallel. So we have standard flood management steps, that is the river and coastal floods, storms. We established key parameters defining the hazard magnitude, develop evacuation protocols based on incoming hazard magnitude. Third, we established the hazard magnitude versus return period, or estimate that, because then we have a time series we can work with. We can develop models of flood modification by alternative protection schemes. We link that to our land-based assets and damage cost functions. 6, we have construction codes for scheme works to be effective. 7, we have the, if you don't mind, please. We establish the cost of protection options. Then we try to deter development in the high-risk areas using measures such as insurance surcharges, planning measures, or compulsory flood proofing. Now, comparing that with tsunami flood protection, steps 2 to 5 transfer directly because that we have the same problem with flooding, whether it comes from tsunamis or from storm surges in particular. And finally, another click, please. Thank you. Another click, please. Thank you. So storm flood planning must cater for walls of water, so-called, from extreme events. And these may involve tsunami-like surges, such as the meter-high waves generated by controlled dam break tests in irrigation canals in the 1970s. Pictures, please. There we are. So that's an irrigation canal we used to do some testing, and as you see, there is this wall of water can be generated by sudden operation of gates, and we track them numerically just to get a model. Next, please. The largest canal was a hydro canal, not an irrigation canal, and they got to be very big enough, in fact, to see from space. You can see, hopefully, in the Pukaki Canal there, you just see a little thread from space, which is not very obvious, but it can actually be seen. Probably higher resolution, see better. Next, please. In these canals, surges of 1 meter in height can travel depths of 10 meters for several kilometers. And these are comparable in scale with tsunamis and estuaries. Next. Next, please. Thank you. So if we're going to have unpredictable wave behavior of that scale, we would not only put several $1 billion of project infrastructure at risk, but there'd also be a significant risk to the community. So we did a major test program as the canals are progressively commissioned, and we succeeded in developing software models and validating with high accuracy. As you can see there, the measured results were a little lower than the predictions, but that's partly because we started a little low. The initial conditions were a little low, and that transferred throughout. But the accuracy is very good, both in the timing and the height of the waves. Next, please. So going back to step one, we've talked about the other ones we've covered, but we haven't mentioned step one yet. That requires an incoming hazard magnitude index for coastal floods to be established. Without this, we can't without this, to take the place of upstream flow peaks, which we use for river flood hazards, events cannot be ranked. So we want to go on. We want to rank events for start, for evacuation protocols to be predefined, because when you're in an emergency situation, a flood is coming in perhaps 1 hour from the sea or from up the river. You can't be expecting the emergency managers to be discussing multivariate probabilistic analysis, even if it has been done in advance. The whole thing has to be simplified down to some kind of index of, and then you would like to be able to tell the emergency managers that this flood is bigger than the 1955 flood and smaller than the 1998 flood or something like that. And you just want to be able to say bigger or smaller. So ranking is also a necessary basis for time series analysis to be used in parallel with that developed for river flood risk management, where it's all done by time series analysis. So we can say one river flood is bigger than another by comparing the peak flows, because that is the magnitude that the magnitude index that's used. But can we say that one tsunami is bigger than another? How can we do this? Next, please. So in the Indian Ocean, 2004, the big tsunami that went through there, the initial wave height at the source was 6.7 meters. That was the displacement of the seabed, vertical displacement of the seabed. Satellite measurements showed wave height of about 0.6 meters and 3 kilometers of ocean depth. That was in the middle, crossing the middle of the Indian Ocean. And there were 2 satellite measurements picked that up then. Tide gauges in the Maldives showed 1.5 meters at Malé and 1 meter at Gun, but the maximum coastal run-up was over 10 meters in Sri Lanka and up to 30 meters in Sumatra. So what's the wave height we are comparing with other tsunamis? We can pick between 0.6 meters minimum and 30 meters maximum. Public warnings often refer to expected wave heights with a clear assumption that a greater wave height would represent a greater hazard. But if there's no consistent definition of what a wave height means or where it's going, where it applies, one suggestion has been to take the wave height as being the wave at mean sea level, above mean sea level at the shore. But could predictions of a height defined that way ever be related to real observations? Next, please. So we had two significant local tsunami events. 1947, March the 26th, we had a magnitude 5.8 earthquake. May the 17th, magnitude 5.6 event occurred a little further north. So there's the March one there. This is the east coast of the North Island of New Zealand, as you can see there. And the other one was there. They weren't magnitude 5 to 6 are not remarkably large earthquakes. They both produced extreme local run up the coast, up to 10 meters in the March event and up to 6 meters in the May event. The 10-meter one, next please, was there at Tatapuri. Just read the 10 meters there, small writing. So we can't just talk about a single shore run-up because it varies obviously quite considerably if we're trying to warn people about their district. We can't just give a general predicted shoreline wave height. That is not useful. So next, please. So we've had a good look at the 10-meter wave run-up. Just how did this come after a mere 5.8, magnitude 5.8 earthquake? So we see the initial development of the wave. This is the blue line here is the upthrust or the seabed displacement reconstructed by GNS, our earthquake modeling specialists. And then we've got a minute, 0.5, 0.6 minutes, 1.2 minutes, 1.8, 2.4, and 3. And you can see the wave rapidly collapses here. The sea is directly above the seabed, is pushed up by the seabed and the earthquake to the same height. And then it's also lowered here by the other part of the rupture event. And then this rapidly collapses by sending waves off in both directions. And this one rapidly fills up as these waves arrive. So it's there's a transition there. Next, please. So the previous plot continues until the tsunami reaches the coast. But here you're getting up to a period about a meter high, and then it suddenly gets close to the coast of the beach, and it gets up to about 3.5 or almost 4 meters high there. And that's a bay tapering to a point there. Next, please. Next, please. Yes. So if the coast is rising steeply as at Tatapuri, the model wave will reflect back, roughly doubling in height to match the observed 10 meters as it does. So once it gets to the end, it'll reflect back, and you get, here's your 10-meter wave according to the simulation. But elsewhere along the coast, the same wave did not exceed 5 meters in height. So the wave height at the shore is as much influenced by the local conditions as by the incoming wave. Next, please. So we propose a definition of the tsunami wave height. Classical wave theory thinks about the cross-section of a wave. There's a long crest heading perpendicular to the screen, and that's nothing much is changing in that direction. So they only consider classicists only consider the two-dimensional plane of the screen, and that's where all the variation of interest is happening. So channels of tapering width, such as in Tatapuri or Hangzhou Bay, for that matter, are not considered. So that restricts classical analysis to the outside boundary between shallow coastal and deep oceanic waters. We just can't go on talking about solitary waves when you get close to the coast, because the width of the wave is changing as well as the depth. That's the width perpendicular to the screen. But in the classical theory, outside that boundary in the oceanic waters, the potential unit energy per unit thickness of the wave is simply due to the elevated water and is therefore reckoned from the undisturbed level indicated. So it's a relatively simple analysis, and if the wave has depressions, that also has potential energy, so that although eta is negative, the eta squared still contributes a positive amount to the potential energy. Next, please. So solitary wave theory, this is in the ocean. We have this, which will be familiar to most people working with solitary waves. It's a standard textbook there, and that's the formula given. And it produces a curve like that, which travels unaltered across the ocean at great speeds. In the case here, 1,000 meters depth, the speed is something like, yes, is about 100 meters per second, or yes, 100 meters per second. Deriving the wave height, sorry. So next, please. So textbook analysis developed by Busanesque in 1872, which was a great achievement. So we have the classical analysis, which shows that for a wave of that type, the capital H is 3 upon small h, and the formula is there. This is the potential energy V, which we previously derived. That can be actually found for any shape of wave. It doesn't have to be a solitary wave, just by numerical integration of a recorded signal from some kind of depth gauge, or indeed a surface. Waves can now be observed by drone, for example. So capital H is the height of the solitary wave profile peak, and so we have a simple scaling from the energy, potential energy, to the height of a solitary wave peak. If the measured tsunami profile approximates a solitary wave, then capital H will be the actual wave height at the point of measurement. But if the wave doesn't resemble a solitary wave in shape, you'll still have an H value, which you can use as an index of the height of the incoming wave. Next, please. So the choice of the standard depth, we have to compute the standard wave height, H0, and that depth should be deeper than the point of transition from oceanic to coastal waters. So with suitable choice is 1,000 meters. Read that. Next, please. Conclusions. Tsunami are physically comparable to flood waves with one problem. Two this is a lack of a widely accepted tsunami magnitude scale. This is really what we're talking about in this paper. Wave heights are used now, but they're so loosely defined, they often differ by over an order of magnitude within the progress of a single wave. Next. Definitive procedures needed to standardize reference conditions. That's what we're really producing now. Solitary wave theory is proposed to express the energy of an incoming wave in terms of reference wave height. So we have a direct translation from energy to a reference wave height. The standard depth contour is proposed to be the point of transition, a suitable choice 1,000 meters. So then we can go directly from incoming wave energy to reference wave height. Next. And if the tsunami profile approximates a solitary wave, this will also be the actual wave height, but it doesn't really matter if it's not. Next. I'm sorry, I can't read that on my screen. You'll have to read it yourself. Thank you.
Yeah, it says.
Thank you.
Yeah, it says it gives a suitable index for hazard magnitude. Thank you, Dr. Burnett, for your informative presentation.
Next, please. Yes, just
Okay.
Click again for the final. Thank you. Yes, that's it.
Okay. Thank you for wonderful presentation, Dr. Burnett, with your experience, especially highlighting many of the case studies, and especially Indian Ocean also, tsunami 2004 you have highlighted, and New Zealand tsunami, and also mentioning about that how tsunami heights are recorded even after tsunami, giving all these accounts of after tsunami, and then later on that you have given a theory to estimate that what are the tsunami height, and also how much it can go, run up is there. You have given a theoretical estimates of that, which I suppose and I'm sure that from civil engineering fraternity, those will be very much interesting. Of course, we are familiar with riverine flood, but working with the tsunami, and which is an approximation, which you have made also in your conclusion, that approximation of the tsunami magnitude, which we also know that how difficult it is, and tsunami is a rare event, but you have given a spectacular decision about the measurement, energy, height, run-up, which are able to make us that how to measure the hazard due to the tsunami wave. So this is in total a complete discussion as well as your experience that you have shared. We are thankful for your time as well as contribution in this manner. And I could not see any such particular chat box, but in case it comes from the about 270 plus participants are there, whenever their chat box they will be writing, I would request you to just see through, or we'll let you know to spend some time in answering them over the chat box. And otherwise, the kind of just only our current experience that we had with 11 March, that earthquake, tsunami, and nuclear disaster that happened in Japan. And we all know that how the tsunami wall that got overtopped, whatever estimate they have made, but 6 meter high wall was there, but it has overtopped by 3.5 meter. And the documentation as well as extensive studies and research from Japan and as well as throughout the world, we all know that how it has badly affected. But right now that now it is about already 10 years gone, but rehabilitations and missing people, many things, many reports are available in the net, as well as many discussions are available. So I would say that to the participants also to see those important documents wherever they find it useful for their research. Thank you, Dr. Bennett, again.
Thank you. If there are any questions,
Okay.
perhaps they can be passed through
Yeah, sure.
through the organisation, and I'll be happy to respond in writing.
Okay. Now let us go to the third presentation today. Professor Raghu Murthugadde, professor at University of Maryland. And so he is BTech in Aeronautical Engineering from IIT Bombay and PhD in Mechanical Engineering from Columbia University. Researcher at NASA for 7 years and faculty at UMD, University of Maryland, for 20 years. So we have a versatile characteristics, no way related to civil engineering, but we are fortunate to have you, Professor Raghu, to share your multidisciplinary from the experience, especially on early warning that you are going to give us. Welcome. Now, floor is yours.
Okay, can you hear me?
Yeah.
Okay. Can you see my screen? Can you see the PowerPoint?
Yeah.
Okay. I changed my topic a little bit because I ran through all the talks and I saw that there is all the traditional hazards, but health was not touched so much.
Okay.
So I decided to give a talk on health, but the approach is exactly the same. This is what is being developed under the World Climate Research Program at certain time scale, which I'll talk about throughout the talk. It's called Ready, Set, Go framework. Essentially, India has invested in, almost 500 crore rupees in the last 10 years to improve weather and climate forecasts. And the results are beginning to show in terms of improved heavy rain event forecasts, heat wave event forecasts, and so on. So when we talk about early warning systems, when we talk about Ready, Set, Go framework for health or agriculture or disasters and so on, we usually talk about looking at the longer forecast, like a seasonal forecast, and ready all the system about rescue systems, resource allotments, where droughts may come, where floods may come, where diseases may come, and where extreme events may happen, and so on. Could be waves, cyclones, etc. Set is the so-called extended range, where it's called S2S, sub-seasonal to seasonal. So weeks 2 to 4. That allows you to get more ready in a place where you are going to expect really the disaster to hit. And then Go is a few days time scale or even few hours time scale. If, for example, Mumbai is going to flood or Bangalore is going to flood, you kick up all the resources there, and whoever is in charge is given all the information about which particular place of the city will get heavy rains and floods. And even using GIS and digital elevation maps, you can even create tools that can navigate street by street to see if some hospital has to be evacuated, if some school has to be closed, if some old people have to be rescued, some building has to be taken care of, and so on and so forth. So I will apply that approach to health and show what are some of the problems and issues that remain. So in India, unfortunately, we still lead the world even compared to some of the poorer countries in terms of waterborne diseases. Air pollution gets a lot of attention. 30 of the most polluted cities are in India, as we just read in the last few days. But waterborne diseases, India also leads in diarrheal diseases, infant mortality, morbidity is not even counted. So if you look at the general drainage basins, we have some 5,000 kilometer coast here. If we include Andaman and other islands, it's almost 7,200 kilometer long. And INCOIS, which does a valiant job of forecasting many things, is beginning to get into coastal water quality and so on. So that's just touching on a couple of issues of water quality on the coast. This is a data for harmful algal blooms from 1908 to 1950, and this is for 1950 to 2009. And you can see that the number of spots with various types of algal blooms has gone up, which is consistent with the warming, the increased rainfall, especially the extreme events, and the urbanization, deforestation, etc., which tend to increase runoff and also increase nutrient pollution, agricultural activities, runoff from the cities, sewage release, etc. So all those create anoxia, hypoxia, and harmful algal blooms. And all these harmful algal blooms infect and cause problems with the seafood that we are getting, whether it's shellfish or finfish and so on. And especially because lots of subsistence fishermen are catching fish, and we don't track very well the quality of the fish or the health impacts, and the data is always a big problem, of course. The other thing is also, if we look at inland water bodies, of course, India has huge pollution problems because of human use, because of agricultural runoff, because of lakes getting polluted by plastic, but also with lots of chemicals and so on. This is data that's showing trends for lake harmful algal blooms or water quality degradations. And you can see that there are some places like here where the impact on water quality is supposed to be decreasing, whereas it is getting worse over here in the north central India. So we have to figure out what it is that is changing the water qualities, how they are related to not just rainfall amounts and rates of rainfall, but also agricultural activities in both Kharif and Rabi seasons, and also whether dry periods are also creating pollution that we don't expect, and so on. So we can get more specific than that in these general terms. That here, this is some work we did with between the University of Maryland and Indian Institute of Public Health in Gandhinagar, where there was good data for enteric fever, which is basically typhoid. And it is showing Surat, this is Ahmedabad and this is Surat. I hope you can see the labels here. It goes from 1995 to 2017. They are just a couple of 100 kilometers away from each other. And yet you can see the variability of enteric fever incidences, and even the low frequency variability is remarkably different in the two cities. Okay, and it turns out that the impact of climate events like El Nino and so on are somewhat different also in the two cities. And you can see here box plots for each month in terms of enteric fever. And you can see that Ahmedabad seasonal distribution and the variability around the mean, these are the box and whisker plots, as most of you probably know, versus Surat. They are remarkably different as well when you look at the mean seasonal cycle. So we have to figure out where this low frequency variability is coming and why this increase in enteric fever in Ahmedabad has occurred since about 2005 for more than a decade, whereas at the same time, Surat has shown a decrease. And Ahmedabad is actually a richer city. Surathkal is poorer and has more slums, population in slums. And yet we are having these disparate typhoid outcomes. So this gives you a sense that the distribution of rainfall, populations, sanitary systems, and the way cities invest in treating wastewater before releasing it into various groundwater systems or other systems have to be closely monitored for health outcomes. And what we learned from COVID is that health is now a major disaster. India leads in the loss of labor, productivity loss, the warming, for example. Productivity of human beings is supposed to be optimal at 13 degrees centigrade. We are nowhere near that. We are much warmer. But we have kind of become used to working in very hot temperatures. Farmers will wake up at 4 o'clock and work, and then take rest in the hot afternoon and then go back to work. So these kinds of morbidities and labor loss can be improved if we can reduce these impacts on health by actually developing these ready, set, go framework of early warning systems, which amounts to basically taking the forecasts, skillful forecasts being made by IMD, developed at NCMRWF and the Indian Institute of Tropical Meteorology in Pune and so on, but issued by IMD. How to get that to the last mile. In disaster management, you talk about people on the ground who make decisions when there is a flood coming, tsunami coming, or cyclone coming. Same thing has to happen for diseases as well. And what COVID has shown us, which is one of the biggest disasters in terms of affecting the global population and bringing all the systems down, and putting tremendous pressure on everything we know as a lifestyle: education, socializing, traveling, healthcare, accessibility to food, transport. Everything is affected, and many things will be probably permanently changed, even though that's hard to say, because if you look at the impact of the 1918 flu, which killed 50 million people, now you don't find much impact remaining. So how long will it take for the society to bounce back? What are the resiliencies in the system? And the worst news is that we have not actually developed any system to manage this kind of disaster if we get hit again, in terms of collecting data, sharing data, people movements, infections, all these things. We haven't actually built systems, or we are not on track to build systems. Already we are rushing back to create incentives to bring the economy back, which means get people to travel, get people to mix, get people to socialize, go to movies, go to restaurants, and so on. So we have to manage those kind of human natural system interactions very well. So this is just showing another example of our study where we looked at 150 most populated metropolitan locations across the world. I will zoom into India, which again has lots of cities which are being exposed to extreme heat events and extreme precipitation events. This is, I hope you can see anyway, this is a global mean. So looking at population increases typically, and exposed population, which is shown in this blue line here. The A is for extreme heat events, and this is for extreme precipitation events. So Indian monsoon is changing dramatically. Onset is changing, withdrawal is changing, rainfall distribution is changing, and so on. So the exposure to extreme events in heat before the monsoon period, now in March, April, May, and during the season in extreme rainfall events are both increasing. But more specifically, if we look at seasons, fall, winter, and spring and summer, various cities of India show up here. Hyderabad, Delhi here. I cannot see my own screen here. All kinds of Zoom things show up. Hyderabad again here. And in spring, you have Chennai, Bangalore is there. So each city is having a season-specific exposure to rainfall events and heat events. Chennai doesn't get so much rain in summer months, whereas Bangalore does, Mumbai does, and Delhi gets rain a little bit later, but Delhi has much more heat events than other cities, and so on. So we don't just need an early warning system. We need very region-specific early warning systems. We have to be very clear about which cities getting the worst health disasters in which season, and then build our ready, set, go framework to fit into those season-specific solutions. All of these need tremendous data, and we are not collecting enough health data, or if you go try to work on health data may exist with hospitals, with the agency that manages district level health. There are certain requirements on registering deaths, cause of death, and so on. But if you want to access those data, it is almost impossible. There is distrust of researchers. There are issues of intellectual property sharing, and so on. Somehow, there is coordination needed at national level, at state levels, at district levels, and down to actually neighborhood levels to collect data and share data. For example, in cities like Pune or Bangalore, asthma in children is going up, asthma among old people is going up. So these early warning systems will allow you to actually be very specific to say, next few days, pollution will be very high. So if you are going to let people, children play outside, then monitor the children who have asthma problems. This is completely doable. This kind of information can be produced, but we need to take the data and do not just relations with environmental parameters. We may also need to do, recently India has announced that they are releasing they will allow high resolution geospatial data. So applications of GIS to layer the data, environmental data, health data, socioeconomic data, because not everybody will get affected the same way by this health pollution. For example, rich people may just turn on the AC and say, no, there is no pollution issue. They will mostly travel in cars, whereas poor children will not have access to AC. They will have to travel on bus or walk and so on and so forth. So exposure itself within even a one city block can differ greatly based on these kind of socio-economic details. The example of forecasts being issued, for example, by the IMD developed at IITM by groups of Sahai and so on, show these kind of examples, observed relative frequencies of heat waves week 1, week 2, week 3, and week 4. This is observed and this is forecast probability. Above this line, you have some skill that is usable for such early warning systems that I just mentioned. So if you have for several weeks the skill of 0.6 or above, this is incredibly useful information. You can really give very reliable probabilistic information to issue what are called no regret decisions. So you just you don't have to close schools or shut down transportation, but you just tell people that you have to be careful, heat wave is coming, so take the bus, don't walk, or go in your car, or be close to have enough water, hydration, etc., etc. Okay, so this is another example of the same. So we are making really good progress, and this is another example of the IMD forecast from last monsoon season. You can see that this is forecast for tomorrow, 2 days later, 3 days, and 4 days later. All these flood forecasts, they were very accurate, and decisions are taken. Sometimes there are issues. For example, in Mumbai, oftentimes there is a shift in the forecasted flood warnings from IMD. Oftentimes it is a day late. So schools are closed, but rainfall has already happened. So this kind of bias correction is needed, and they are very doable. But again, you need data to do those very reliably and very accurately. The other thing that needs to happen to manage health disasters and reduce vulnerability is to look at socio-economic vulnerabilities. This is some work we did with colleagues at IIT Bombay and a graduate student Vittal Bhatt, so Sudhimal Ghosh, Subhankar Karmakar, and myself, and so on. And this is just showing socioeconomic vulnerability to natural hydrometeorological hazards, which means extreme rainfall events. It was done with 2 census data, 2001 and 2011. And the difference is very telling. Over 76% of the grid boxes that we looked at down at taluka level, okay, very good data. You can go to taluka level. This was done at district level in the end because of some other issues. You can see it's districts. 76% of the districts actually showed reduced vulnerability at the same time as hydroclimatic hazards have gone up in number. Why? Turns out that one of the key ingredients there was educating women allows them to better understand the warnings and deal with the warnings and make decisions that reduce the vulnerability of their family to hydroclimatic hazards. So these are the key factors that I would want to leave you with, that collect data very regularly, monitor events, use forecasts to develop early warning systems. And in fact, the Global Commission on Climate Adaptation has talked about how climate adaptation for a country like India, where climate change impacts are already here, is early warning systems. We don't have to worry about what will happen in 2100. We want to worry about 2030 for energy and food and water and health. But these early warning systems at this ready, set, go framework, season by season, is very critical for India. And this, I think, should be considered as part of the disaster management that we always talk about, only in terms of earthquakes, tsunamis, and waves, and floods and droughts and so on. So comprehensive monitoring, modeling, and predictions are needed. Lots of it is happening. The last mile problem of getting forecasts to decision makers is very critical. And training them to use these forecasts effectively is important. Regional and coastal and inland labs with local partnerships with schools like NIT, NIIT, and so on are needed, crowdsourcing of data, etc. Totally doable because there are regional specificities of health outcomes and also other disasters, because health outcomes, especially waterborne diseases, are always related to floods and droughts as well. We need data centers and we need a regional earth system prediction, which takes into account the environmental factors as well as vegetation, mosquito population, health, and so on and so forth. So I will leave you with that. I think I'm hopefully on time, but if there are any questions, I'm happy to answer.
Thank you, Professor Raghu, for giving very, very data-specific and early warning requirement based on the database that you have highlighted, that you have been working, even being outside India, but you have been working with Indian data and Indian institution, and also interpreting various data being collected by India Meteorological Department. And you have rightly mentioned about more data requirement and more specific warning to be given, especially on the health-related aspects. And really, we are inspired by your concern as well as talk, and as well as projecting that what level of data that we need it, and entire world that they have been now enchanting with data collection, big data, artificial intelligence, and many things. And that way, you know that India also going on through our IITs and through our young researchers and all together working on that. And as far as some of the comments I can see from my side is that you have mentioned about you have mentioned about 1918 flu, where crores of people at that time, you know, First World War and those things. At that time, we still remember. And this time, having so much of development, even in the developed country, where data management and data collection, health issues, immunity, and their surroundings, everything is being monitored. Whereas you know that several databases have been generated and several papers are coming up in the international journals, the kind of response that India took, not with the voluminous data that which can be easily interpretable, but the kind of immunity and the kind of COVID positive, you can say, which is going on, or negative cases, and especially the impact on the mortality. It is such a Pandora box that, you know, it will take years or decades together to analyze that how we are living in this condition, where a lot of data that we are not knowing, even we have not yet explored yet, but still the kind of database or the kind of inference that Indian cases or the country in this part, Southeast Asian, that whatever way that we are living in, I would like to have your say on this for the audience, on behalf of audience.
Yeah, I mean, I think COVID-19, if you remember last year, this time we were just beginning to have the ramp up of the cases. Unfortunately, we are again seeing some sign of increasing cases, whether we have a second wave or whether vaccination will take care of it. But fortunately, after October, November, or somewhere around November, cases began to drop. There are issues with testing and numbers and data and so on. But knowing that the healthcare system didn't get overwhelmed and people were not dying so much in large number, which is not easy to hide, genetically somehow coronavirus didn't seem to affect us as much as the Europeans and the Americans. Maybe there is some genetic factor there, but nonetheless we are getting a second wave. So we have to be careful about relying on luck every time, because unless I was invited to write a editorial on what didn't work, and it appears in current opinion in environmental science, which I can share with you people if you want later. But this idea of India collecting data, sharing data, and monitoring the situation, and getting people to follow mask rules, social distancing rules, and so on, we have just been lucky this time. If next pandemic comes and we are not so lucky, then that is not going to be much fun. So we must learn our lessons and not think that we got away with something, that this will not happen again. Because with climate change, we have a very good petri dish for health issues, because warming creates good conditions for microbes to grow, and water distributes the microbes. So we have very warm pre-monsoon temperatures, which makes everything grow. And monsoon comes and starts distributing the microbes, and suddenly there is increase in all kinds of diseases that are associated with rainfall, not just floods. Floods make it much worse. So we have all the diseases that are still there. So it is just a matter of time before another pandemic hits. So we must learn very carefully our lessons this time and make a very good national plan for health disaster, monitoring, risk reduction, early warning systems, all the way down to the last mile at the taluka level and at neighborhood level. Hospitals have to be involved, doctors, health workers, NGOs, schools, everybody has to be involved.
Yeah. Okay. Thank you very much. I have one thing from the chat box. There is one thing actually here in Sudan and in Africa with the easier African intro, we are facing the same data availability issue. So how long this forecast you describe is available? Like you try to say that whatever forecast based on the IMD data and other data that you have taken from the. So
yes.
One of the participants, Mohammed, I'm not able to see, but he is asking that
yes.
warning or prediction for what period or timing can it be a little bit more specific?
Yeah, so the Ready, Set, Go has 3 time scales. The first one is the seasonal time scale. So every 10 days or so, centers like IMD issue forecast for the next 3 to 9 months. Okay, that is used as an outlook. And then there is what is called extended range, which goes from weeks 2 to 4. And then there is the weather time scale, which is, let's say, day 1 to 10. So these are the 3 time scales. And the good news is India has invested a lot, and it trains many countries in Africa, Bangladesh, Sri Lanka, and all these, Nepal, in using our forecast. So if you are interested, you can contact. I'm not sure of the geopolitical sensitivities of our specific countries, but it is worth exploring to see if your country can also take advantage of the training and the forecast. So India shares the forecast with the countries, and then you will need local data to translate the physical forecast into health warning systems. And the same system can be done for agriculture. We have some work with IIT Bombay also on how to schedule irrigation based on weather forecast data, how to save up to 30% of the irrigation water. It is doable for crop modeling, for energy, solar and wind, which we are doing planning and so on.
Okay. Okay, thank you very much. As far as the country that in Africa or Sudan and even Middle East country, as far as data sharing and other things, India has made a lot of coalition, like in coalition in disaster resilience infrastructure, that is a newly created, and there is another Solar Alliance coalition also is there, which is headquartered here, CDRI, like that. And data operability and shareability, as you know, you have been working with India and surrounding country, that it is all through many international organizations like WMO, World Meteorological Organization, and also many databases that which are being taken from the government of India, like EMDAT, then CRED data or Swiss Ray data, lots of data, like you have also have shown many sources of the data. So lots of data are now being shared, and so it is up to the country or up to the experts that who can really work on that. As far as an IDM is concerned also, we are also collecting data from the district level, taluka level, especially on the resources like disaster resource network or knowledge networks. A lot of this data also being collected at many nodal organizations. So I think now it is all data being flowing from here and there. So we have to make really palette for solving our local problem as well as regional problem. So thank you, Professor Rogo.
Thank you for the opportunity. Thanks for inviting me.
No, it is our pleasure, as well as we are obliged really for keeping you here from aeronautics and mechanical engineering, and then working on health issues and playing with many data that which are really effective, and also in the early warning area that you are thinking of, which is beyond. Again, I am saying that I'm on the civil engineering domain, but now we have to, in the risk of DRR, disaster risk resiliency, civil engineers, we have to now encompass all these areas also. Thank you.
Thank you. Bye-bye.
Okay. So we have here Shreya Shvi from Global Earthquake Modeling. She did her dissertation on doctoral dissertation in NITK Surathkal. So congratulations, just only in 2019 you have, and you have joined this global earthquake modeling, which we know that in Italy, and many experts, they have volunteered their time. And we have noted that you are doing postdoctoral scholar at IIT Gandhinagar. Yeah. And then at present you are working as a seismic hazard modeler at the Global Earthquake Model Foundation, Pavia, Italy. And so your her interest is in structure and soil dynamics, structural and soil dynamics. This is again an interesting area. And also engineering seismology and earthquake engineering. So she has given many guest lectures, and also faculty development program organized by Sardaya College of Engineering and Technology, Thrissur, and also AICT, All India Council of Technical Education sponsored STTP at Rangasamy College of Technology. So we have here, I think, the youngest keynote speaker of the I think entire VCDRR. So taking the torch and also working on global earthquake modeling, which we know through various work that they have been doing. It is really, we are fortunate to have you here on this August gathering. Please, floor is yours.
Yeah. First of all, good evening to everyone, and it is definitely my pleasure to interact with experts like Chandan Ghosh sir and Professor Shrivalza and Ravi Jaka sir. I was just scrolling down the participants who are there, and I'm really privileged to be interacting with all of you today. So I'll just start sharing my screen. So I hope my screen is visible now.
Yeah.
Okay. So as you may already know, that today I will be talking about estimation of local site effects. So what I would be presenting is a little bit of what I have learned when I just started in the domain. And later on, I will slowly move towards what I worked on during my PhD and also through other collaborations with MTech students and with other potential collaborators in our area. So the title of my talk would be Estimation of Local Site Effects, Lessons from the Past Earthquakes, Current Practices, and Future Trends. Okay, so I'll just give a brief overview about what is local site effects, just in case if somebody in the audience is a little bit new to this topic. So basically, whenever we talk about local site effects, it's about understanding how a local material would interact or would respond to a ground shaking. So usually it's not like when a ground earthquake occurs, all sites will behave in the same manner. So there are chances of different sites behaving differently. So that is what we are trying to address when we talk about local site effects. So commonly, as you can see here, one is amplification, liquefaction, and landslide. So liquefaction and landslides are more like secondary effects of an earthquake, and geotechnical damages are quite common when we encounter a large magnitude earthquakes and so on. And like I was saying, the spatial variability is the most interesting aspect of site effects when we can see. So the diagram or the schematic representation on the right side, as you can see here, so this is how different sites would respond. So here, if we consider the extreme left case, wherein we are considering a site which is situated on a solid bedrock, but it has more like an hilly terrain. So in such cases, if in the event of an earthquake, such sites are more prone to landslide rather than amplification or something like that. And if you consider a poorly consolidated sediment, as it is here, so in this case, first it leads to amplification and then it leads to liquefaction. However, if we consider a solid bedrock, as you can see here, so this will here the buildings located on these kind of site conditions will be subjected to a mild ground shaking. So the buildings may not experience much of shaking in this case. And again, if we go for a well consolidated sediment, the shaking would be moderate. And if it is a poorly consolidated sediment, sediment, then there will be settlement of the buildings. And if we go for a water saturated sand or mud, then obviously there will be sinking and the damage is going to be severe and so on. So what exactly does this local site effect do? Is that whenever we consider a ground motion, there are three important components, such as amplitude, frequency, content, and duration of shaking. It is these three components which usually get affected during due to local site effect. So before going further, I would like to just show some of the earliest evidences of local site effects that we have. So one earlier evidence, actually, the Japanese started to understand that there is a possibility of local geological conditions or local site conditions being impactful in early 1930s itself. But we saw a major evidence during Niigata earthquake, or it could be the liquefaction damage during Loma Prieta earthquake, as you can see here. And the bottommost figure, what you are seeing here, this is actually strawberry field, wherein you can see some sort of sand boils, you can say that. And these are sand boils are usually common, and sand boils have been observed in New Madrid earthquake and San Francisco earthquake of 1989 and Christchurch earthquake in New Zealand. So this is one of the recent examples. So whenever we talk about local site effects, it's the Mexico earthquake of 1985, which actually becomes very prominent. So during Mexico, in this particular highway, you can see that a longitudinal crack has been developed, and you can see a cavity as well here. So there is actually a sinkhole in the middle of the road, and this is mostly because of the subsidence of the soil in that particular area. And this has been observed since 1985 Mexico earthquake. So coming to the Indian scenario, so I will be showing some of the photos. My PhD supervisor, Professor Katta Venkatramana, he had the privilege of visiting Bhuj, actually Kutch region of Gujarat immediately after Bhuj earthquake. So these are some of the photographs which I have borrowed from him. So this is the ground settlement due to liquefaction near Kandla port, as you can see here. And there was actually a telephone pole, and which has actually collapsed because of ground subsidence and also liquefaction and also sand boil, as you can see here. And apart from this, during Sikkim earthquake in 2011 and during Nepal earthquake in 2015, there have been a substantial amount of geotechnical damage, we can say. So this is about the history of geotechnical damages during some of the major earthquakes in India. And there are a lot more than I've shown here, actually. So in order to understand the overall concept of site effects here, so whenever we talk about a ground shaking, which is observed, be it in such a one-story building or in a multi-story building like this, so you can actually decompose the ground shaking into three major components. One, we call it as source. The second one is the path, and the third is the site. So when we speak about source, it is the source which is actually causing the seismic waves or generating the seismic waves. And the propagation path is the path through which it travels, and then finally it comes to the site, which is actually a crucial aspect when it comes to the damage that could be caused to the built environment. So now here, as you can see, we are not actually dealing with source or path in today's lecture, but we will be focusing only on the site part here. So the type of site response also depends on the geometrical structure in a site. So if we consider just the center of this site, what you are seeing here, which will look like the one on the extreme right corner, the top figure of the right corner. So here it's just composed of layers with different shear wave velocities, and this is how the wave tends to propagate through the layers, and it eventually reaches the surface. But if we consider the edges of these, which we usually call it as a basin or a valley, then the seismic wave actually hits here and it undergoes multiple reflections, and this we usually call it as basin generated waves. And because of this basin, the duration of shaking is prolonged, the amplification is increased. So these are some of the effects when you consider the shape of the site to be somewhat like this. And another case is if it is a topography, like you can see here, that if you have an outcrop, or it could be just a hilly terrain or topography. So then also again, we see an increased amplification. So it always depends upon the geometrical shape or geometrical conditions of your site as well. So usually we call, how do we quantify the site effect is that whatever the ground motion intensity, it could be PGA or PGV or spectral acceleration, irrespective of the quantity that we are actually interested in. So the spectral quantity or the intensity measure, which is recorded at the surface, to the ratio of that at the reference site. So sometimes it could, the reason why I have mentioned it as a reference site is because sometimes it could be the bedrock, or sometimes it could be seismic bedrock or engineering bedrock, or it could also be at some particular layer that we are interested in. So we always keep it as a reference site, and also finding out a bedrock depth is not so easy. So until and unless we have very skilled techniques for that. So the reason why we juggle so much with site effects is because whenever we are doing a seismic hazard estimation, we want to incorporate these site effects into a seismic hazard framework. So one of the easiest and straightforward method to incorporate site effects in seismic hazard is by using the information that is available through digital elevation models. So these models are freely available, and it is available for the entire globe, and anybody can access it easily. So we use these, this is actually the topography of a region. This is actually Mangalore. This is the work which I did during my PhD. So this is basically the topography near the Mangalore and the Kerala stretch. So I have just considered the topography, and through that, Allen and Wald, they proposed a correlation wherein they could correlate the slope derived from this topography to the VS30. So this is the VS30 map which I've generated for my study region. And so after that, I used the VS30 map and also the PHA, which I had previously computed, and I could generate the site factors. And this is basically a surface level hazard map that I was able to generate. So I have not gone in much detail in the specifics, because in the end, I will give you the details of the publications which you can refer to. And so this is somewhat how the end product is going to look like. And this is the most simple, straightforward approach. And anybody, even you don't need any site specific information, first of all. And this would always aid people in at least identifying which are the potential sites where you can expect maximum amplification. So accordingly, you can pick the sites wherein you can go for a site-specific investigation too. So this type of estimation techniques could act as a preliminary or initial framework. Next, so coming to one-dimensional ground response analysis. So as many of you may already know, it's about that we apply an input bedrock motion or an input motion at a bottom of the soil profile, and we simulate the wave propagation through different layers of the soil, and then we try to see how much the input motion has been amplified. So whenever we are trying to do this, there are a couple of informations that are needed or that goes into the engine in order to compute these. So first is the soil modeling. So we should have an idea about the soil parameters and also about the input motion. So I will talk about these input motions in detail. So some of the commonly required soil parameters would be the shear wave velocity or unit weight and the shear strength properties of the soil and so on. So overall, in site response analysis, there are a couple of classifications. One is it depends on whether we are doing site response analysis in time domain or frequency domain, and we are interested in the linear behavior or a non-linear behavior or an equivalent. We can try to call an interim between linear and non-linear, and we can call it as equivalent linear. So, and also sometimes there will be a water table in the soil profile. So whether we are taking care of that pore water pressure or we are not taking care of the pore water pressure. So depending on that, also there are different classifications, and whether we are going for a one-dimensional or a two-dimensional or a three-dimensional. Again, so the choice of different types of site response analysis actually depends upon what exactly we are looking at in the end product. If you're going for a very critical infrastructure, then we have to go for more advanced and more sophisticated techniques to estimate the site response. So I will be talking mostly about one-dimensional site response today. So a couple of input parameters that are needed when it comes to just the soil modeling part is, one is you should know the shear wave velocity profile and shear modulus and so on, and damping. And the next part is about the input motion that is needed. So sometimes what happens, sorry, just a minute. So this is kind of an end product as to how it actually looks. So this is more or less the input, and this is how the output will usually look. And so sometimes what happens, we have some of the data missing. Let us say SPT end values are quite available for most of the sites actually. So how can we make use of such information and still do or derive some meaningful outputs through site response? So there are a couple of correlations which have been developed just for the Indian region and also for other parts of the world, wherein they try to correlate SPT end value with the shear velocity. So if this is how your typical profile looks like, and you have an SPT end value, you can always estimate shear velocity through the correlations, and also you can handpick, or you can have some rationale for selecting only certain correlations and then estimating the average shear wave velocity profile. And so, and coming to the input motion, so there are a couple of options when it comes to the application of input motion into any particular site. So one of the common method that I have used is one is through empirical Green's function technique that we call it. So if at all, if there is a site for which we have weak motion data, what we call it as lower magnitude events recording, then we can kind of upscale it, assuming that the same site will be subjected to an earthquake from the same source, but the earthquake magnitude will be much higher. So under that assumption, we can always use empirical Green's function technique, or we can also use the ground motions which have been recorded in different parts of the world, but with a matching tectonic regime. So there are a couple of options when it comes to the choice of input motions. So now the most important thing whenever we try to incorporate site response into PSHA is that how do we take care of the uncertainty aspect? So as you may know that in uncertainty, there are two, the one is aleatory and another one is epistemic. So when it comes to aleatory uncertainty, and we are talking about the profile information, as we know that the geographical variation or the geotechnical variation of the site sometimes offers us certain challenges. So we cannot estimate for one particular particular site and then assume the same kind of site response for an entire region, because the soil is quite varying. So that kind of uncertainty is what we call it as aleatory. And so in order to take care of that, sometimes what we do, we have a single profile, we are going to randomize it through some of the previously established models, one by Toro 1995. So a similar experiment was done wherein we have tried to have a number of realizations of a given soil profile. So our experiment was to understand how many number of profiles or how many number of realizations are required so that we can make a stable estimate. So our study suggested that we need a minimum of 20 to 22 realizations so that we can achieve a stable estimate. And also sometimes what happens whenever we are estimating VS or whenever we are estimating other soil parameters, there will be certain amount of uncertainty. So that is more or less towards epistemic. So we can take care of it by improving the measurement techniques or taking multiple profile readings and so on. In a similar way, when it comes to input motions as well, whenever we are dealing with applying an input motion to a soil profile, we can use 5 recorded ground motions or 7 recorded ground motions and so on. But there have not been any specific guidelines about how many number of ground motions are actually required for site response. So one of another experiment that we did along with one of our MTech students is that we try to understand how many number of ground motions is enough, or because if there is no end, and finding so many ground motions for a region where we do not have any recorded ground motion is quite difficult. So from our experiment, we could see that up around 7 to 11 ground motions should be enough whenever we want to perform site response analysis, because there was a criteria for performing time history analysis for structures. So like we need 5 to 7 ground motion records, but there was no specific guideline for site response analysis. And so this is a part of my PhD work that I've done. So this is a new approach towards characterizing site amplification. So many of them have already previously proven this point that VS30 is not a sufficient single proxy for characterizing the site. So here in the extreme left, as you can see, this is just a 3 different sites, but with same VS30. But as you can see here, these sites behave differently for the same seismic excitation. So that is when I thought that we should probably characterize it based on the soil type or site type and so on. So and also I was more inclined towards investigating the nonlinear site amplification. And so whenever we talk about linear and nonlinear, if the amplification, what we are observing, is independent of the input motion, then we call it as linear. And if it is dependent on the input motion or the intensity measure of the input motion, then we call it as nonlinear. So this is a plot wherein I have plotted amplification versus the input acceleration at the base of the soil profile. So based on this, I did sort of curve fitting, you could say, based on the different soil types, and I have tried to estimate how the amplification actually differs for different site types itself. And also in our experiment, I could say that we observed more nonlinear behavior in sand, maybe for the data that I had collected. So then after having developed the equation 1 was the site amplification model that I had developed. So this was later further incorporated into the seismic hazard assessment, which I had already estimated for a reference soil condition. So this is how it actually looks after being incorporated. So there are different techniques as to how we can integrate site effects into seismic hazard assessment. So most of the techniques that we are practicing in India is deterministic. So my dissertation was more focused towards making it a probabilistic approach, and it was not previously attempted, especially in the Indian scenario where we don't have much of site specific data, but we still would like to know at least a preliminary guidelines of how we can go ahead. So this is one of the attempts that I did. As you can see here, this is for the rock and this is for the surface. And then I generated a response spectrum for different soil types, as you can see. And it was also compared with other codal provisions as well. As you can see here, our findings, actually, they pretty much agree well with that of ASCE 41. But with respect, if you see BIS 1893, it stops somewhere here in the bottom, but our estimations are quite high. So there is a need to improve the codal provisions, I would say. And also I could generate region specific design spectra based on the because we had site data from more than 50 plus sites just with between Kasargod and Calicut, that is the northern Kerala portion. So we could generate design spectrum for the study region after categorizing it into different sites based on the NSPT value, because our IS 1893 categorizes the sites based on NSPT. So I had to categorize our sites to based on. Yeah.
I think you have to conclude now.
Okay, just a minute. Yeah. So some of the computer codes that are available I've shown here if we are interested in 1 dimension or 2 or 3 dimensions. Some of them are open source and some of them are quite commercial. So coming to the future directions for estimating the site response, like I said, sometimes we may not have sufficient input motions for conducting site response. So in such cases, we can use an RVT base. This is something that has not been investigated in India so far. This method has certain drawbacks, but I think with certain corrections, this method has a lot of scope, at least within India. And there is a need for improving the site classification, and more importance should be given towards a probabilistic approach for incorporating site response and SHA. So those are some of the publications that if audience are interested, I would be happy to share.
Oh, okay. So thank you. Of course, you represent the global earthquake model, Selfie, and I think audience also may expect that what this GEM means. What just a brief, can you say about just briefly in 1 minute?
Okay, so global earthquake model, as the name itself suggests, we are a non-profit organization who is working towards global mapping of seismic hazard, and also we have developed our own engine which is called as OpenQuake, and this software can estimate seismic hazard using classical PSHA or event-based PSHA and scenario-based PSHA. And apart from that, we offer consultation for nuclear projects and bridges all over the world. We work all over the world, and we have partners all over the world. And so that is.
Is there any Indian partner other than you? You are working for them.
Actually, last time when they did the global mosaic, which was one of the projects of GEM, wherein they're trying to do the hazard mapping for the entire world, they collaborated with Abhishek from IIT Guwahati and Kaustubh Dasgupta from Roorkee, and a couple more people within India. Somebody from IIT Bombay was also part of it. Someone from IIT Delhi was part of it.
Okay. Okay, thank you for a nice presentation on taking really deep into the site effects and also bringing out the rudiments of soil behavior under various earthquake. And you have taken a very extensive study on that and taking examples of 1964 Nigata earthquake or 1989 Noakhali earthquake or even Bhuj earthquake. And also taking into that amplification that you have shown, that where Indian SA spectral acceleration versus time period, where it stands, and what are the zonation that we know in our country, zone 4, zone 5, and whatever design that we are making using zone 5 and whatever earthquake force that we are calculating, and our designer, they are doing it using computer. But well, those design means in terms of reinforcement, when they are even at this, we take hardly 8 to 9% of the, if we take the maximum zone 5, we take hardly 8 to 9% of the total vertical gravity force. Whereas in other countries, they take more than 20-25%, which has been reflected in your spectral acceleration versus time period. At the same time, you have also shown in one of your publications, in one of your presentation, and also it is observed in Mexico or even in Japan, acceleration recorded by seismometer or whatever seismic observatories, more than 1G.
Yes.
Even 2G, 1.88G.
Yeah.
This is one aspect. On the other hand, even amplification has gone up by 17%, 17 times, 18 times, when in Mexico earthquake in 1985. So while these are the observations in the field, when we are seeing all are nonlinear, then how your analysis takes care of those cracks which you have shown in the beginning, how those can be simulated from a real experiment or real simulation through your the 1D, 2D, 3D analysis.
Okay. You're talking about the simulation of the cracks.
Because all is being done in the elastic range, you know, shear wave, shear, everything in elastic component. Non-elastic part is still very complex and a lot of iterations are required. We cannot take it. But things fails, whatever features that you have shown in various earthquake and liquefaction, these are all in a nonlinear domain.
Nonlinear, yes.
And we are yet to explore those things.
Yes.
To simulate.
In the studies that I have done, I have tried to do equivalent linear, and recently when as I'm working with GEM, we are working in non-linear as well now, because we are working on one of the sites in South America. So that is Cali, it's a city in Colombia, and also Chile. These are the regions which have experienced a lot of non-linear site amplification as well. So we are slowly moving towards non-linear, but like you said, doing a non-linear analysis is not so easy until and unless we have site-specific data. And I'm not just talking about shear wave velocity profile or something. We need the soil modulus curve itself, and we want the damping curves of those particular soil type. So I think that is one of the ways how we can move forward. We need more site-specific information and more accurate site-specific information.
So there is a lot of scope to work in this area, especially in soil structure and correction.
And also for some of the soils that we see in Mangalore, like laterites and all, so soil like that, we don't have a curve, a modulus reduction curve or a damping curve. So even it, and also for a lot of these man-made landfills that a lot of studies are focusing on nowadays, even for them, we do not have the site-specific curves, and in such cases, using the standard curves may not fetches the actual site response. So even there is a lot of scope in going more towards laboratory testing of specimens collected from those kind of sites.
Okay, so it is one again for in our all participants and everyone. There are lots of our participants, of course. Many key resource persons are also there. I hope that let us see that. In the disaster risk reduction or disaster resilient society that civil engineers are focused to, let us see that how far we can go, taking global earthquake model also in mind. And of course, let me see how exactly, there is one question quickly, how exactly strain rate dependent dampings and modulus models are incorporated in nonlinear analysis in your presentation?
Okay, so nonlinear analysis is basically time dependent. So wherein it computes the change in the strain and change in the shear modulus with respect to time. To be more precise, so that and also all these modulus reduction curves or damping curves are essentially strain dependent. So they are usually correlated with respect to strain. If that was the question, if I'm understanding it correctly,
Okay, more so, and in fact, one Muhammad PM Ahmed, he said, please share your publications or your scholar URL in the chat box. So, okay, with this, I think we are almost right on time, and it is a fantastic time that that we had in the last 2 hours, having 4 presentations. And so now with this, I give it to Sivalsa, conference organizer.
Thank you, Professor Chandan Ghosh. So thank you for very efficiently chairing and moderating the question answer of this keynote session 4. And thanks to all the speakers for accepting our invitation and delivering excellent talks. So thank you very much. So we have speakers from different continents and different age groups. You can see, as you rightly said, Shreyas is the youngest in our list, and we have Dr. Barnett, then Dr. Raghu and Dr. Roxy Matthew. So Dr. Barnett has, I think, 4 decades of experience. He's chairing the IAHR, that is one of the very prominent society of especially the water resource people, no hydrology people. I think more than 70 years. So he is chairing the flood committee. So we are enjoying the talks by all the speakers. So I hope all the participants are also enjoying the lecture. And slowly we are breaking the ice and we are getting connected to each other as days pass. So I hope, because as we said, we declared this conference on 13th October 2020, International Day for Disaster Risk Reduction, and we will be ending on 20th March 2021, which is the International Day for Happiness. So I think, as we come together, interact each other, our happiness level will increase. So with these words, once again, thanking all the participants. So I will just share my screen showing the keynote session 5.
Yep.
It is scheduled tomorrow, Indian time, 9:30 to 11:30 a.m., 18 March 2021. The session will be chaired by Dr. Arvind Jha, and we have 4 distinguished keynote speakers: Dr. Arjun from NIT Silchar, Dr. Darren Chian from National University of Singapore, and Dr. G.R. Reddy. He is a distinguished scientist retired from BARC, Mumbai, and also president of Association of Structural Rehabilitation, and Dr. Basantaraj Adhikari from Tribhuvan University, Nepal. So we look forward to see you all tomorrow 9:30 a.m. Please join 10 minutes before the session. So I hope with this we can end this session formally.
Yeah.
Thank you. Thank you all.
Thank you.
Yeah. Bye.
Bye. Bye.
Bye.